Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is AISC 360 2016 Steel Connection Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. As far as the content over the next hour today, I do want to give a brief introduction into finite element analysis connection design and the overall concept. This is a little bit different than some of the other connection design software out there. So we'll go ahead and learn a little bit more about the concept that we take within RFEM. We'll then move on to our example, which is shown over here on the right-hand side with a simple steel frame. We'll talk about the connection component input utilizing the steel joints add-on within RFEM. We'll also discuss the joint template options or the ability to create your own user-defined connection options. And of course, we'll be taking a look at the results, including the FEA submodel that's generated, as well as the buckling analysis. And finally, you'll hear me say this several times today, that a huge benefit of doing the connection design within RFEM is the ability to integrate with the full member design as well. So we'll take a brief look at that at the end of the example, utilizing the steel design add-on. So we might be wondering, well, why would we utilize FEA for steel connection design? And obviously the biggest benefit is going to be the design of non-standard or unique connections. So most likely you have a solution for very basic or standard connections. A lot of software offers this, or even hand calculations. But when we look at this connection over here on the right-hand side with a lot of different components going on, it becomes a little bit more difficult. So this new steel joints add-on within RFEM allows us to consider the components and the members both in plane and out of plane in one single FEA model. We also can consider complex loading. So if we are modeling the entire steel structure within RFEM, we can apply any of the member loads or unique loading scenarios to the structure itself. The member internal forces at the member ends at the joint will simply be used for the connection design. So no need to integrate those member end forces into an external program. Again, everything is done within this single file. The submodel is automatically generated underneath the hood of RFEM. So this really doesn't require an expertise level knowing how to create these FEA models. They are rather complex, but rather if you just have a general FEA knowledge, and you can go ahead and utilize this capability within the program. We also will perform the AISC design checks of these connections for our bolts, our welds, and our plates, but we will take it a step further to create a second submodel to carry out the buckling analysis. So we'll be able to view the different eigenmodes and failure buckling modes of this connection, as well as the critical load factors. So we'll see that a little bit further in the example today. So all in all, we'll be able to calculate more precise results with less assumptions for these unique connection types. And even if we are using hand calculations or additional software to try and carry out this connection design, we can certainly utilize RFEM and the steel joints add-on as a validation tool. So now moving on to the RFEM steel connection design concept. Again, a little unique in comparison to a lot of the other programs out there. So we will probably generate the entire steel structure in RFEM. It's not required, but this is one approach that we could take. And with these one-dimensional members, such as beams, columns, braces, these are actually going to be automatically converted into an FEA model, a submodel that we see over here on the right-hand side. So you'll notice that those beams, column, braces now are two-dimensional surface elements that we can further mesh. Also, the bolt elements are going to be converted to 1D beam members as well. And we'll transfer the forces of these 1D bolt members back to the plate elements, the 2D surface elements, with what we call spoke members. So we'll be able to view that within the submodel in our example today. Welds are also converted to 2D elements for a stress design, as well as one-dimensional rigid links to transfer those forces again back to the plate elements. Now, we typically would model our steel structure with a linear elastic material. The program will automatically convert this linear elastic material to a nonlinear plastic material. So we'll be able to account for the yield strength of these steel materials themselves. We also will have some geometric nonlinearities that are automatically created. And what I mean by this are topics called surface contacts, where essentially if we have two plates modeled together, they can fail in tension so that we have our bolts take over those forces, but in compression, we should see full force transfer. Some of the members, such as those spoke members that are modeled around our bolt elements, will also have nonlinearities applied. Again, automatic member end force transfer. So this is certainly a big deal that we're not taking these member end forces, having to export them out of the program or this file, but rather these member end forces, again, that we see over here on the right-hand side are automatically accounted for based on the member that is modeled within the RFEM. We also will, as I mentioned, carry out the AISC plate, bolt, and weld design. So full connection design for these elements, despite how complicated the connection may be. And we are taking it one step further with that buckling submodel. So we'll be able to view today the different failure modes of that buckling submodel and the critical load factors. And finally, the integrated member design within RFEM. Of course, we can get the connection design, but the ability to design the members themselves, and not just steel, but any material that we offer. So you could combine this connection design with concrete, aluminum, cold form steel, even topics like fabric tensile structures. We could do the steel connection design within that same file. Okay, so we will begin then in RFEM here with our initial example. When we create a new model, we will give it a model name. The type of model here is going to be in a 3D environment. So although we just have a simplified 2D frame here, we still are accounting for all forces in and out of plane. Under the second tab, so for those of you who are not familiar with our program, RFEM is the base program. This is where we can fully model, load a structure, and get the full static analysis. But if we want to do a more advanced analysis like dynamics, for example, or we want to do design according to the various standards, and this is where we would need to activate these optional add-ons. So you would purchase the add-ons that are specific for your project design. Now for today, we'll be activating here the steel design. So this carries out the steel member design according to the AISC, and of course the steel joints for our connection design. Under the third tab, we will generate the load combinations automatically according to the ASCE 7. We have added the 2022 standard, so that's available here. The steel member design will be carried out according to the AISC 360 2016. And under our fourth tab here, Standards 2, the steel connection design will be carried out also according to the AISC 360. So once all of this information is input into our base data, as you can see here for the sake of time, I've already modeled this simple 2D frame here. So let us just quickly go over some of the information already shown. Well, if we turn this into wireframe view, these members, as I mentioned, are just standard one-dimensional elements. So this is pretty usual for any FEA program, that when we model columns or beams or braces, they're represented by this single line only. But if we turn this into rendered view, we get a better understanding of what this line represents. Now, we also have here the materials assigned to these members, and currently these are all A992 linear elastic materials. We also have our cross sections. You can see here the columns are assigned as W14 by 48. And for my beam members, these are W12 by 35s. But I also have applied a small taper at the beam member end. So if we double click on this member to go into the beam dialog box, Under the second tab here, section, we do have the ability to set a taper at the member start or the member end and other multiple options here. So I'm currently applying this taper at the first 25% of the member length. And we also can align the taper to the top of the member, for example, and this picture over here will update accordingly. So as mentioned, the beams are primarily W12 by 35, but where this taper occurs at the member start, I took that W12 by 35, I created it as a user-defined section to simply increase the depth. So now we'll linearly transition in the first 25% of this beam member back to the W12 by 35. So that's a little bit about what's going on with our members. So turning this back into wireframe view to quickly explain our support conditions, we have a fully fixed support down here at the bottom, which was just applied by utilizing the assign nodal support up here in my toolbar. And also because we are working in a 3D environment, I went ahead and put some additional spring supports up here only in the lateral global Y direction. So we'll account for maybe additional members framing in to give that lateral stability at the top of our frame. And finally, we want to cover the loading. So we have 3 simple load cases for today, and we can see these within our drop-down box up here at the top. If I turn on my loads, my dead load is 0.5 kips per foot, applied as a member load. When we look at our live load, same concept here, just with a reduced magnitude of 0.3 kips per foot. And then a very simple lateral load here for our wind load case with 0.3 kips per foot at the front side and 0.15 kips per feet at the rear side. Going into our load cases and combinations dialog box, we will once again see here under our load cases our 3 simple load cases for today. Dead, live, and wind category was set accordingly to the ASCE 7. The program is automatically going to generate 2 design situations for us. We have here our LRFD design situation and our ASD design situation. This is really nothing more than just grouping together all of our factor load combinations according to the ASCE 7 for this first design situation. And we can click on this little info button here to see the code references to those load combinations directly. Now notice that these are used within these optional add-ons that we turned on. So steel design and our steel joint or connection design. I will be utilizing these design situations. I'm carrying out my design according to LRFD for today. Now we also have this second design situation, which is just simply grouping together our unfactored load combinations. I'm going to use this for my serviceability checks for my steel member design, but we really don't need it for our connection design because serviceability is not something that we're going to check. Now, alternatively, if you were carrying out ASD design for both your members and your connections, we could go ahead and turn it on here and maybe we deactivate it for the LRFD design situation. But again, moving forward with LRFD design, we'll go ahead and leave these options as default. And finally, under the load combinations, you can see here the individual load combinations listed out based on the load cases I have defined. All of my factored load combinations are shown here in orange, which belong to that first design situation. And then we have our unfactored load combinations shown in red that belong to the second design situation. So just keep these design situations in mind. We'll come back to them a little bit later on. So now that we have fully reviewed this model, let us begin by defining our first connection. So because I have activated the steel joints add-on under my base data, we now have a folder option over here on the left called types for steel joints. Well, currently this is empty, but I can right click to create a new steel joint. And initially, I want to select the node that I would like to apply my first connection. So we can graphically select node number 6, or I could directly input the number here into this dialog box. Both of my members were automatically brought in. Looking at this second tab. So remember that we are going to more or less extract out this submodel for our connection design and run it completely separate from our steel frame that's happening here in RFEM. And because of this, we need to fully support one of these members in that submodel. So we'll go ahead and utilize the support for the beam over on the left. Now the type is set to ended. This only means that if all of these members simply end at this connection, then the type would be set to ended. Now, in another scenario where we maybe had a continuous column passing up through here, but it was modeled as two separate members back in RFEM, then we would have an additional type option available to us in a dropdown called continuous. Under the Components tab, this is where we begin to build up our connection components. And we could certainly individually do this with our connection database here, our component database. And we see each one of these components that we can individually input, such as end plates, or we can input in fin plates, cleats, maybe plate-to-plate connections for beam splices. We also have stiffeners and haunches, and then we have some additional modifications up here that more so relate to the geometry. So we can make member cuts, or we can add in openings or notches into our beam elements. But rather than inputting in these individual components, we could also take advantage here of our library options. And within these joint template library options, we have 4 general categories, including rigid connections, pin connections. We also have truss connections and brace connections. So beginning here with the rigid connections, we have additional subcategories such as beam to column, and so on. And within these subcategories, we have additional template options. So looking at the beam to beam, we have an end plate to plate. We have an end plate to plate with a rectangular hollow section. For today, we're going to utilize this option plate to plate with a haunch. So when I click apply template here, it's automatically going to apply these components from this library to my specific members here within my RFEM model. So I can click OK, and now we see these individual components listed out here and applied again to the members within the RFEM model background. Now, we could certainly add on with the individual components here and just use the library as a starting point. We'll certainly need to make some modifications here to our geometry, but once you have your connection set and you utilize this connection quite often, it's always recommended to save this under your own user-defined template as well. So you can see here within this button, we could give the connection a name, set the filter categories and subcategories, and now that connection will always be available for any future RFEM model. So that could certainly be helpful if you don't want to redefine the geometry changes or components every time. So starting off with the first component, you can see here it is plate to plate. We are connecting both members 1 and 2. We can make modifications to the position, but we'll go ahead and leave all of this as default. Now we do need to define the material of these plates. I already have A36 defined within my RFEM model, but if you did not, you could just access our material dialog box with these 3 buttons here. So within the material dialog box, we can further activate the material library. Over on the left, utilizing our filters to steel, to the AISC 360, then we could go ahead and choose whichever relevant steel material we'd like for this particular component. Again, utilizing the A36 that's already been defined, I will modify here the thickness of my plate. So we can go ahead and change each plate to 0.5 inches thick for a total thickness of 1 inch. And now we need to define the plate offset. The offset just means what is the distance from the top of the plate to the top of the flange, and then the bottom of the flange to the bottom of the plate, as well as left and right. So starting off with the top offset, I'm going to modify this to actually a negative 0.375 value. I'm going to drop this plate down below the top flanges here on my beam in the event that we have some type of sheathing material that we don't want it to interfere here with these plates. Now, as far as my bottom offset, we'll go ahead and modify this to around 5 inches. And then we have the offset on the left and right. right, which I will set this at 0.5 inches for the left, and I just hit enter on my keyboard, and 0.5 inches on the right. Now, the dimensions of the plate will automatically update here. Next up is our bolts. So we have here the designation of the bolts within our dropdown. We will select A325. And in the drop-down box next to this, we can then select the diameter. So we'll choose 3/4 inch diameter for our bolt layout today. Then we have the number of bolts in the horizontal direction as well as the spacing. So currently we have 2 bolts in the horizontal direction, one on the left and one on the right. So we'll go ahead and stick with a total number of 2 bolts. The input here in our second column is just simply the horizontal spacing. So the first spacing that we would want to input in here is just going to be the distance from the edge of the plate to the center of the first bolt. So I can input in 1.75 inches. I hit space on my keyboard. The next distance is from the bolt here to the bolt on the other side, and that's going to be 4.055. And then if I just hit enter, the program is intelligent enough to set that additional dimension here from the center of the bolt to the edge of the plate. Now, keep in mind that the program will attempt to center these horizontally, so you may not need to make any changes there, but if we want to adjust that spacing, this is how we would do so. Now, as far as the bolts in the vertical direction, currently we have 5 bolts, but I'd like to reduce this to 3 bolts instead. And obviously, once we update this, we need to adjust our spacing. So we have the vertical spacing. The first input option is going to be from the top of plate to the center of my first bolt, which will be 3.5 inches. I hit space on my keyboard. The next spacing will be from this first bolt to the second bolt, which will be 5.5 inches. I hit space again, and we need to lastly define the spacing here between bolt number 2 and bolt number 3 as 5 inches. I hit enter on my keyboard. The program will populate the last spacing here from our bolt down to the bottom of the plate. Now, is the thread located in the shear plane for our bolts? If so, we leave this option turned on. If not, we would go ahead and uncheck it. And finally, we move on to the welds. So we can see here that these welds are labeled within this first column, but as I scroll through them here, they're also highlighted graphically. And if I didn't want to apply any one of these welds, I could just simply uncheck it here, and that weld would be taken away from this particular connection. But leaving all the welds as active, you'll also notice here that the default weld type is going to be a double fillet weld on both sides. But we can easily modify this to a fillet weld at the front side or the rear side or even a butt weld. So we'll leave all these as double fillet welds. Our weld strength is selected from this drop down. We'll go ahead and stick with the default E60. And now we need to define the throat thickness. So currently we input the throat thickness in terms of inches. We do plan to also add the weld leg size, as we know this may be a little bit more common when we're designing AISC connections. So keep in mind that that should be added in the near future. But for now, we'll input in the throat thickness at 0.25 inches. And a little trick here, if we hit the down arrow key into this next cell and I hit F8, all the way down, this will copy the cell above it. So we're now going to apply 0.25 inches for our throat thickness to all welds on these plates. So that will really sum up now our first component and any of those geometry changes. We now want to move on to our second component, which is a haunch. So we see it's highlighted over here on the left-hand side, and we're currently referencing member number 1 and the particular web. And we want this haunch to be extended then to our plate shown here. The material is set to A36. We do want to modify here the thickness to maybe 0.5 inches. We can also modify the width and the height. So I'll modify the width here to 12 inches, and we should see that graphically display here. The height is going to be 5 inches. And you'll also see that the program automatically included a flange here as part of my haunch. If I wanted to get rid of that flange, I could go ahead and use my drop-down box here to select the no option, and that flange should disappear. Now, finally, we have our weld input for the haunch itself, and we have two welds, which we'll go ahead again and leave it as a default double fillet weld on either side. But our first weld is on the underside from the plate to the bottom flange, where we will modify the throat thickness to 0.25. And our second weld is going to be from the haunch to this end plate here, which again, we will modify that throat thickness to 0.25 as well. So looking at our haunch on the right-hand side, again, we're complete with this second component. We move over here on the right-hand side, and we want to make those exact same changes that we just did to the left-hand side. So we'll modify here the thickness to 0.5 inches. We want to modify the width to 12 and the height to 5 inches. And then we will also want to select no flange here in our drop down. And finally, we will modify the throat thickness to 0.25 for both of those input options. So realistically, this connection is now complete. And again, if you utilize this connection quite often, save it to your user-defined library so you can pull it open with these modifications already set. The final thing to do with any connection is to check out this fourth tab, the plausibility check. So we see here it's a green checkbox with no errors found. If we had any issues, such as maybe bolts overlapping welds or plate elements, or maybe we have a weld extending beyond a plate, these would all be flagged here so that we could take care of those errors before we move forward with the calculation. So now that this connection is complete, we can click OK here. And what we should see is that graphically, we're going to represent this connection here within the main RFEM model. Now, to explain a little bit further about what's going on, you'll notice that when I turn this to wireframe view, we still have those one-dimensional members. And notice that these members are still framing from node to node. We're not going to cut off this one-dimensional member where this connection starts. Really, this is just a graphical display of that model that will be acted out and completely calculated separately from this RFEM model. But it is nice just to view in a little bit more detail exactly what's going on. Also keep in mind too, a common question is that the member end forces for this beam will actually be taken at this node. They are not taken at this distance away where the connection will begin. Going back then into the rendered view, we can see this connection here with all of the available components, the geometry changes that we just input. Now, with the display of our connection, we also have an additional option up here in our toolbar where we can completely hide that joint model with this dropdown if we're not interested in seeing it. We also have this simplified joint model, which is just represented by some box type symbols here. And finally, we have the detailed joint model, which is currently default and turned on. So now that we have defined this first connection, we would like to move on to our second connection, which is going to be the tapered beam to the column. So we can yet again right click over here in the types for steel joints to create a new steel joint definition. And we want to graphically select here node number 3. I click OK. The two members are automatically imported in here, and under the second tab, if you remember, because we're creating that FEA submodel, at least one of these members needs to be fully supported. So we'll go ahead and leave the column as fully supported. Under the components, we will take advantage of our library option here. And this time under our rigid connection, we want to modify this to a beam to a column. And within the additional template options over here, many different options, including cleats, maybe we have an end plate to plate. For today, we want to utilize the column with stiffeners. I'm going to hit apply, and yet again, we should see these individual components applied directly to my model. I think we could all look at this connection and be in agreement that this certainly does not look correct. And this is really just an issue of the program not knowing which member is the beam versus which member is the column. And that's controlled simply with our options over here on the left. So in our dropdown for our column, we want to change this to member number 1. And then our beam element, we want to specify as member number 2. And now this connection should look quite a bit better. So we click OK. And just like what we saw with our previous joint, we will now see all of those components individually listed out here. So let us begin with the end plate. And you can see here with the end plate, we are taking member number 2, which is that tapered member, and we are connecting it to the reference member number 1. Steel A36 will be utilized for the material. If we want to modify the thickness, we can input this in as 0.75. And very similar to our last plate element, we would want to define the offsets. So looking up here at our top offset, remember the top of the flange to the top of the plate, we'll go ahead and modify this to 0.5 inches. When we look at the offset at the bottom here, we will modify this to 1 inch. And then we have an offset on the left and the right hand side of those flanges, and we'll go ahead and set this as 0.25 on the left and 0.25 inches on the right. Now looking at our bolts, again, clearly we need to make some modifications here. So we will be selecting a 325 from our dropdown. The diameter of the bolt is going to be 7/8 inches. We are going to leave this as 2 bolts on either side, so 1 bolt on the left, 1 bolt on the right. The program again has centered these, so I will go ahead and leave these as default options now. As far as the vertical bolts, currently we have 3 shown, but I want to increase this to 4. So once I input the 4 bolts, we'll make some modifications here to our vertical spacing as well. The first input option is from the top of the plate to the center of this first bolt in the vertical direction, which will be 3.5 inches. I hit space on my keyboard. We now need to define the spacing from bolt number 1 to bolt number 2, which will be 5.5. And I'm actually going to apply 5.5 inches to the additional spacing 3 times then between all of these bolts. I then hit enter on my keyboard. We see all of those update graphically here. We'll leave the shear plane and thread turned on. And finally, we have our welds. So we have the weld at the top flange, again, leaving the fillet weld on either side as default with E60 strength. We'll modify the throat thickness to 0.25 once again. We take a look at our weld at the flange, or sorry, at the web here. We'll go ahead and modify this throat thickness at 0.25, and we do the same thing for our weld down here at the bottom, modifying this thickness to 0.25. So now our end plate is complete. So we'd like to move on to our second component. So remember that not all components necessarily insert a physical object into this connection, but there are components that have to deal with modifying the geometry. And one of them is called a member cut. So without a member cut, which keep in mind that for any one of these components, we can always not consider them by unchecking them here. Without that member cut, you can see here that the column just stops essentially at the middle of that tapered beam. So this member cut will actually extend this column up to the top flange of the beam. So we're taking member number 1 here, and we're going to make that cut by referencing member number 2. Now, the cutting method is set to a plane, and the cutting plane has 2 options, either closer or farther. So when I set this to closer, notice that the column is automatically going to be cut off here at the bottom flange. But when I use the option farther, we'll go ahead and extend that column to the top flange instead. Now, additionally, the cut of this column is matching the incline or the pitch of my tapered member shown back here in this 2-dimensional frame. If we want this column to be completely straight across, we can use our drop-down options here to choose perpendicular instead. So now notice that that column is cut straight across, not considering that incline. We'll go ahead and match that pitch by changing this back to parallel here, and now that will match, again, the top flange of my tapered beam. We also have the ability to set an offset. If I have this offset set at 0, it just simply will make that member cut to match the top flange, or I can set this offset to negative 0.75 inches, which will extend it slightly above the top of this beam. So that's all that is needed for our second component. We now want to move on to the stiffener. So we see here this stiffener applied, and the stiffened member is referencing member number 1, but we want to apply these stiffeners based on referencing member number 2, the beam. The material is A36 once again. Perhaps we want to modify the thickness to 0.5 inches. And we are applying these stiffeners based off the member plate flange number 1 here of our beam. So everything is parallel to that top flange. Alternatively, if I didn't want it to be parallel, I can make it perpendicular so that we have the stiffener going straight across. Of course, this doesn't make sense here because our column isn't extended up high enough. So we'll go ahead and change this back to parallel. We could also add in an offset to move the stiffener up or down. And we also have the ability here to set the stiffener on both sides, or within this drop-down option, we could choose just the left or just the right. And finally, as far as geometry, we have a small chamfer here. So we want to set this dimension to 1 inch exactly. Finally, we have the weld. So just like what we saw with our other weld input for our additional components, we're going to leave this as a double fillet weld, E60, with a throat thickness of 0.25. So this is just connecting that stiffener back to the column. Now, we also have our last component here for our stiffener shown here at the bottom flange. Again, if I didn't want to account for it, I could just completely turn it off. Or if I wanted to delete it altogether, I can use this red checkbox. So I just make sure that I'm selected here under that particular component. I delete it altogether. The reason why I wanted to show you is that we have a nice feature here for existing components that if we right click, we can copy the component to the end of this list. And this is a huge advantage if we have made a lot of modifications to our component and we don't want to input in all that information again, we just simply make a copy. Now, currently, the second stiffener is sitting right on top of the first stiffener, so that's not ideal. But what we can do here is just to simply move it by referencing instead of flange number 1. We'll see here we want to select flange number 2, which is highlighted here as I select it within my dropdown. Now, currently it's set to parallel, so it matches the angle here of that taper. But if we wanted to modify this to perpendicular, we can do so. Now we see that stiffener shown here at the bottom in the perpendicular position. And if we wanted to modify the thickness to something smaller, we could do so here at 0.375. So now this fourth component is now complete. Again, checking the plausibility, no errors found. That's great. If we had any issues with geometry or anything else, the program would notify us here. So when I click OK, we should now see this connection applied over here to the left-hand side. And what you will notice is that we actually want to apply this exact same connection here on the left-hand side to the right-hand side. And rather than redefining all of those additional components and a new steel joint, the program's intelligent enough that I can go back to node number 3 here, my connection that I just defined, and in addition, select node number 11. And I click OK. So we have an identical layout for our joint template here. It's just simply the mirror image of the other side. So again, if you have the exact same connection details, but it's just slightly oriented differently within the model, you could certainly apply multiple nodes to the same joint definition. All right, so we are almost ready to move forward here with our analysis in our design. But one thing that I did want to cover before we do, if we go back into the steel joints and we go into edit the dialog box, this brings us back into the dialog box that we have previously been in, but you'll notice here there is design configurations. And there is one option here for strength configuration with a default setting already specified. Well, the strength configuration, if we go into edit this, is specific to the AISC design of our connection, but also that submodel that's going to be generated underneath the hood. And we have to assign a configuration to each one of these joints. And you can also create different configuration settings for different joints. But taking a look at the default option shown here, you'll notice that the first option for my connection design is to also perform a buckling analysis. So we can go ahead and turn this on. Now, I do want to let you know that you have to own the stability analysis add-on in order to carry out the buckling analysis in addition to the actual AISC connection design. So if you want to take it that step further, you do need to own the stability analysis add-on. You don't need to go back to the base data and activate it. Everything is controlled here through this dialog box. We now get an additional tab here for buckling. So in addition to that FEA submodel, we'll carry out an additional submodel for the eigenvalue analysis. And you can see the analysis type is set to a linear analysis, but we also have nonlinear options here. Just keep in mind that obviously that calculation will take a little bit longer if you do apply a nonlinear analysis. We will calculate by default 4 eigenvalues, but you can go ahead and increase this or decrease this depending on how many different failure mode shapes you're interested in. Second order analysis is considered. And finally, we have the limit load factor. So this is a user defined input option here, and it all relates back to that critical load factor. So when the critical load factor falls below 15.0, the program will go ahead and flag you that maybe buckling is a consideration that you need to look at further for your connection. Again, you have the ability to increase this or decrease this factor. It'll make a little bit more sense once we look at the buckling results. So going back to the main tab here, we have here our resistance factors for LRFD design, straight from the AISC standards, safety factors for ASD, and then a lot of this information down here at the bottom is specific to the FEA submodel and mesh generation, for example. The FEA mesh back here in RFEM for our overall structure is going to most likely be entirely too large to apply to this much smaller submodel. So we will go ahead and submesh that to something much smaller, and we have some default options shown in here, but you can always come in and modify the FE mesh settings as well for that submodel. Now, one thing I do want to go into a little bit further detail is the limit plastic strain. And you'll see this input is set by default at 5%. So let us go back to the PowerPoint to discuss this in a little bit more detail. So by inputting in this plastic strain limit, this is going to be used for the strength limit state criteria for all surfaces. And what I mean by surfaces, remember that our one-dimensional members for our beams, our columns, these are all converted to 2D surfaces. So our flanges, our webs, our end plates, haunches, all of these are now 2D surfaces. Well, also, we're probably utilizing a linear elastic material, but the program automatically converts this to a nonlinear plastic material. And with this material model, we are going to reference the von Mises yield criterion stress failure hypotheses. So when we look at the general stress strain diagram of a steel material, we see that shown here, the lower right. We certainly have our linear elastic region shown here before we reach that yield strength Fy. Now, once we reach Fy, we are in the plastic region. Now, ideally, steel is going to behave more like the red line shown here for the physical stress strain curve. But for our nonlinear material model, we actually simplify this into just a simple line element here. Now, the modulus of elasticity, of course, is the slope here in our linear elastic region. But in the plastic region, we assign a plastic modulus of elasticity, which is going to be the linear elastic modulus of elasticity over 1,000. So this is just a simplification that we take with that nonlinear plastic material model. Now, a big question is, why are we setting the limit plastic strain instead of the yield strength in terms of the yield stresses? And the reason why is we're going to have hundreds, maybe thousands of FE mesh points on these submodels. And when a single FE mesh point reaches this yield strength here, Fy, then inevitably we would be saying that the entire connection is failing. when in reality, we know that if a single FE mesh point reaches this yield strength, the load is actually distributed to the FE mesh points around it. And as long as we don't have a huge region of the connection that is yielding, that the entire connection actually won't fail when a single FE mesh point reaches that yield stress. So we want to utilize the plastic behavior of this steel with that internal force redistribution even after we have reached slight yielding. And we do so by setting the limit plastic strain instead, which is shown here within this region. We follow that same slope, and this way we can get ever so slightly yielding, but the entire connection is not being flagged as failing. Now, the default value for that limit plastic strain is set at 5%, and this actually comes from the Eurocode referenced here. The reason we have this set to 5% is because the AISC actually does not give a clear definition on what value we should use here for finite element modeling. It really just leaves it up to the user, the engineer, to determine what that should be. So we set the 5% by default there, but you can always come in and modify this value here. But overall, there have been studies done on this that there really is good relevant correlation to the actual steel plate behavior by limiting the plastic strain instead of the stress. So again, that's what's going on here within our design configuration for all plate elements. This is the only check that we will carry out is by limiting that plastic strain. So once this information is all input into our configurations, the final thing to do is to go back here to our RFEM model and to jump down to the steel joint design add-on. So within this add-on in table format, we have here our two design situations, which we should remember as we covered those earlier. We have our LRFD design situation where we want to set this to the strength limit state for LRFD design. Now, alternatively, if I was carrying out ASD design, then it might look something similar to this, where I use my drop down to carry out my second design situation for my unfactored load combinations according to the strength limit state for ASD design. But I'm carrying out LRFD design today, so we'll go ahead and utilize that first design situation. The objects to design, we will be designing all three connections here. And in a very similar workflow, we also have the steel member design. So I did an entire webinar devoted entirely to the steel member design according to the AISC, which will clearly go into much more detail than what we have today. My point today is just the ability to design the members along with the connections. So we have our two design situations here for our steel member design, and we're going to relate that first design situation, factored load combinations, to the strength limit state for LRFD, and then my unfactored design situation here, ASD, is related to serviceability, so those deflection checks. I will be designing all members here as well. So once we have input this information into the table, we are now ready to go to calculate all. But keep in mind, because we are now introducing these FEA submodels, it does take a few minutes to solve. So it will take a little bit longer than if we just had these steel 1D members alone. So for the sake of time, I'm going to open up an already saved model here that has carried out the calculation. Well, what we should see once we run our analysis and design under the steel joints table here is our results. And we can view the stress strain analysis design ratios by node. So now you'll notice here that I have 3 design checks for each connection. And these 3 design checks include the plate check, the bolt check, and the weld check. And within any one of these specific design checks, such as the bolts here, I can go ahead and activate my design check details. And this is true for both the bolts and the welds. We'll take a look, though, only at the bolt elements. I'll go ahead and expand out my options over here on the left-hand side. I'll use my control key and I'll zoom in here to these equations. So hopefully those are a little bit easier for you to see. But we are checking the bolts for all scenarios carried out by the AISC, including tension resistance, shear resistance, bearing, combined shear and tension, and so on. And then we take the max design ratio here out of all of these, and we'll go ahead and present it to you in that design ratio. But all of the code references are given here, all of the formulas line by line. The variables are listed out here. You can add this information to your printout report. So trying to be as transparent as possible about where these specific checks come from. Same concept for our welds. If we look at our plate check, so this is currently for my connection shown here at the left and the right, which you can see are highlighted. I'll go ahead and open up my design check details here, and you can see this looks quite a bit simpler. And this just all goes back to the PowerPoint slide that we just covered, that for all of our plates, we're talking flanges, webs, end plates, haunches. We are only going to check this limit plastic strain. So we have here the limit plastic strain set at 5%, and then we have our plastic strain from the actual analysis, and we ultimately get a design ratio. So that's going to be a little bit different here for our plate checks versus the bolts and the welds. Now, in addition to the design check details, we also have the ability here called the results in steel joint. So we can go ahead and activate this, and this will actually show us our submodel here of this particular connection. So we're currently looking at the tapered beam to the column connection. And if I scroll here to my second tab, we are viewing the plastic strains for this connection for load combination number 2. And I zoom in here, and at first it really doesn't seem like much is going on. And that's just simply because we're going to gray out the strains that are probably not much of interest. But we do see some higher strains here at the top of the connection. Now, alternatively, we can toggle this to the stresses instead. And this might look a little bit more interesting, that we can actually view the stresses for all of our components here graphically. And of course, where we saw those higher strains, we're also going to see those higher stresses given. So going back to this initial tab, if I go ahead and collapse these different display options here, I have the ability to actually turn off completely my members and plates and maybe my fasteners. And now I can view the stresses just on the weld elements themselves. Or if I'd like to turn on the bolts, I can go ahead and activate here the fasteners, and we see the tension forces and kips given to us graphically. And finally, going back to the display of all of these options, we go back to the stresses shown for all components. Now, in addition to viewing this information here, we have the ability to save this model to our computer. And when we save this model, we can open it up like any other RFEM model. So I went ahead and took the liberty to save that particular connection to my desktop so that we can see what this model actually looks like, that's all being created underneath the hood automatically for us. So here is our exact same connection with the FEA model shown to us here in detail. So notice that the web elements, the flanges, everything was converted to these 2D surfaces. And if we turn this into a wireframe view, you'll see here everything is meshed automatically for us. And perhaps if I go back to my navigator here to turn off the mesh, we can look our weld elements. And these weld elements are a mix of 2D surfaces in order to get the stresses, but we are also transferring forces between the weld and the plate elements with these small rigid links. We also have our bolt elements. So I had mentioned some of this in the PowerPoint, but if we double click here, we can actually see that these bolt elements are represented by a standard beam element. The cross section is also taken into consideration, the diameter here of our bolt element that we've set, as well as the material. And we are going to transfer the forces in this opening where the bolt is passing through with what we call these spoke members. And these spoke members are nothing more than beam elements themselves with a cross section assigned. And everything is optimized here with the cross section and the number of spoke members in order to transfer those forces between the plate element to the bolt and vice versa. We also have a nonlinearity applied here for this beam spoke member that it will fail in tension. So we really want this bolt to bear on to the plate element when it's in compression. But if we have any tension between those two elements, that connection will fully fail. So that's what's going on a little bit underneath the hood is it's really just putting together all of these different elements into this FEA model. And by all means, you have the ability to manually create this same exact connection. We're just taking it a step further with giving you the ability to automatically generate this pretty complex model underneath the hood. A couple more things to touch on if we take a look at the materials. So all of the materials are listed here for our beam elements, and I'll turn this into a rendered view, A992, A36, and even our bolt elements and our welds have the relevant material. But you will see that these are now converted to plastic material models rather than that linear elastic. And finally, if we take a look at our drop down about all the different loading scenarios here, these are our ASCE 7 factored load combinations that are being applied here to the member end. And as I scroll through these different load combinations, we should see these loads update automatically. They're applied here to a rigid plate. So this rigid plate allows the load distribution across the entire face here. So we don't have to worry about topics like singularities because this load is distributed again to the entire face of these elements. And remember too, that we had to set at least one supported member. Well, we can see that support applied here at the bottom of the column. Okay, so that will cover here just the submodel. So let us go back to our frame quickly to talk about the buckling behavior. So in addition to the design, according to the AISC, if we go back to the steel joint design, we have an additional drop down here for the buckling analysis. And looking at the buckling analysis results in table format, we are calculating 4 eigenvalues here for each connection as well as each load combination. So as we scroll through these, it should highlight exactly which connection we're looking at. And also you'll see here our critical load factor. And if you remember, under the configurations, we told the program to flag us if this critical load factor falls below 15.0. So what is a critical load factor? Well, if we're currently looking at our connection here, and load combination number 2. The critical load factor is the value or the factor that you can multiply your loads in load combination 2 before you're going to see some type of buckling behavior. So when we are getting down around to values such as 1.0, this is a very big problem. Anything less than 1.0, the connection cannot handle 100% of the loads before we're going to see buckling. So again, we can kind of set that user-defined value of when to flag us for that critical load factor. What might be interesting too, in addition to the table format, is to yet again launch this results in the steel joint here, and it will look very similar to what we saw before, but there's a slight modification here now that we are viewing our buckling behavior, is that we can actually, instead of viewing stresses and strains, we're viewing the eigenvalue here, or the eigenmode. So we can see that under this particular load combination number 2 and our critical load factor of 12.82, we might be concerned with buckling within the web of our tapered member. If we scroll back up here to maybe our center connection, and we'll go ahead and launch the display here of the buckling behavior. Notice this critical load factor is much higher for load combination number 1 at 31.09. But in this case, we might be a little bit more concerned with the initial buckling of our flanges, with a secondary concern of these web elements here for that center connection. So buckling is certainly something that is not easily accounted for with hand calculations, connections, analytical calculations for connections. So we have the ability here to carry out this additional analysis and determine that if buckling is a concern, do we need to increase the thickness of these surfaces, such as the web members or flanges, or maybe we need to add additional stiffeners with those component input options. So that will sum up then the connection design, but keep in mind that we also did the steel member design. So we can view the results of the steel member design within our table format here and the design ratios by each member. And again, just as we would any other steel model, we can get full design here according to the AISC. Notice that all of the calculations are carried out with each one of the relevant chapters within the AISC. So the ability here to design the members and the connections is just quickly shown with this example model. So that will sum up this example. Now, I know that this was a very simple application, and we might argue, well, I could easily do hand calculations or use my current software for connections such as this. But I did want to open up here another RFEM model with maybe a little bit bigger of a structure here. So you'll notice that we have multiple steel members shown in 3 dimensions. And I even have modeled a couple of concrete platforms within this particular structure. And if I go to the wireframe view, what you'll also notice is that I have defined these joint connections at all of the major intersections here of our steel members. So if we take a look at maybe one of these particular connections, I'll go ahead and create a visibility by this selected object. And let me turn this back into a solid rendered view. Well, when we zoom in here, we can see that this connection is certainly a little bit more complex than what we just saw with our 2D frame. We have beams framing into the column in the strong axis. We also have beams framing in the weak axis. I have added end plates, haunches. We have stiffeners shown here. So quite a bit more going on. If we rotate over here on the right-hand side, we also have these tension-only braces that are framing in according to these, or transitioning from these plate elements, and they are welded to the top and bottom flange of my beams. So we also can carry out, of course, the full connection design here. I'll go ahead and zoom out and rotate this back around. Under the steel joint design, you can see that the design ratios for each of these nodes is carried out. We have 3 design checks here for our plates, our bolts, our fillet welds, all encompassing FEA submodel shown for each one of these connections. And we also have carried out the steel design. Again, all of these steel members have been automatically designed according to the AISC, and I even took it one step further to design these concrete platforms here. So I carried out the ACI design, considering the reinforcement applied. We see a couple high reinforcement design ratios shown here. That's just no surprise, an issue of shear at where these platforms are connecting back to the steel members. But all in all, all-encompassing option here within RFEM to do a multi-material design along with the AISC connection design as well. Now you can download this model as well as the previous 2D frame. I've already put those models up on our website where you have registered for this GoToWebinar, so you can download it, open it up in our trial version, and take a look at it if you'd like to play around a little bit. Okay, so we will go ahead and conclude our webinar today. Just one more point to touch on, and that is kind of where we're headed with some future developments here with our connection design. So I put together a short list, and this list is more so set up so that the top of the list will be released relatively soon. The options shown down here at the bottom will be a little bit more longer term developments. So currently we support all AISC cross sections, and you can even input in user-defined parametric sections as well. You're not limited to only the AISC sections. But the only exception to this is round HSS. So currently we support square and rectangular HSS. Round HSS is currently in development, should be released very soon. A preloaded bolt input that is also not quite ready, but is currently in development for topics like slip critical connections. So that should be available very soon. We also recognize the AISC 360 2022 was released. So we'll go ahead and add any updates to the standards. You have the ability to design according to the 2016 or the 2022 as soon as we implement that. Additionally, we are planning to add the ability to export out the true stiffness of this model back to the main structure. So this joint stiffness is already calculated with this FEA submodel. We know this of the connection. So therefore, we can export out that stiffness for the member design rather than having fully fixed member end releases, fully released. We'll be able to account for the true stiffness there. Base plate design is also currently in development. We will release that according to the AISC and the ACI standards. BIM integration, we will also plan to work on for topics like integrating these connections into programs like Tekla. As some of you know who have been using RFEM 5, we previously had timber member to member connections. So because we've totally revamped this connection design input here within RFEM 6, we also want to add timber member connection design in the future as well. And finally, AISC 341, 358 seismic design checks we plan to also add, but currently the AISC 360. Okay, so this presentation was recorded, and we will go ahead and place that recording on the same web page that you registered for the webinar. So feel free to access it shortly after. Again, these models that I use will also be available for download, and you can access the 90-day trial version of RFEM 6. So this is full capability, no limitations for the full 3 months. It includes all add-ons that you can open up these models. We also have hundreds of models on our website that you can open up and take a look at in the trial version. If you have any questions about today's presentation or any of RFEM's capabilities, feel free to reach us at our Philadelphia office shown here at the bottom. Our phone number is 267-702-2815, and our email to the Philadelphia office is info-us@deluval.com. So we will have many more upcoming webinars. These take place approximately once a month. We will plan next month to give a presentation on cold form steel design according to the AISI. So we just released that. So it's something to look forward to, and you can register on our website at deluval.com under support and learning webinars. As most of you know, I tend to send out a reminder email when these webinars will take place. So keep an eye out for that once we do schedule that cold form steel webinar. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that if you want that PDH, you do need to be present for the full duration of this webinar today. If you watched the presentation with a colleague or in a conference type setting and you were here for the full duration and you are wanting PDH, you will need to request this PDH at info-us@deluval.com. So if you yourself did not register with your own name and your own email address and you are wanting PDH, please send us an email request at the address shown here. Let us know who you watched it with, and we will be happy to issue that certificate. It should be known that the PDHs are not sent out automatically as soon as this presentation ends, but it usually takes up to a day to get those out. So just keep an eye out in your email for that PDH to be sent. And with that said, I want to thank everyone for attending, and as always, we hope to see you at the next presentation. Thank you.